Bonjour. Hello. My name is Luc Rolland, as you can see me here. I will make my presentation about myself and my research, which I can do, which I've done so far, and the topics which are of interest for as far as I'm concerned. So who am I? Well, first of all, I'm a mechanical engineer that graduated from École Polytechnique de Montréal, so it's the largest francophone university, engineering university. It's a specific engineering university. It's the largest outside France, and it's situated in Montreal. Okay, and I've done that in 1985. I graduated with a license of engineering, or what they call in North America, bachelor's of engineering, after 4 years, and then I did a research master's in applied sciences at the same place in robotics. So I graduated in bachelor's of engineering in mechanical engineering general, and I did a robotics simulation master's at the same place in mechanical engineering as well. I then did a long time afterwards, so I finished a PhD in 2004, a PhD at Université Henri Poincaré in France. And it was funded by the INRIA, which is the best research center in automation controls and robotics in France and perhaps Europe. And they are doing things there which are unparalleled in the world. Okay, it's a network of research centers amongst the best in the world. I worked on high-speed milling during that PhD, and I have designed the first robotics simulators to be able to certify these high-speed milling machines. They're using parallel robots. And then I did work on several robot inventions, different places throughout all my careers there. And I have 2 patents which are pending at the moment, the result of the research I'm doing here in Glasgow. Well, first of all, what I worked on is serial robotics, and I still work on that aspect because I just finished a project showing that we could do laser bar manipulations with a microcontroller, a very good microcontroller approach there, with visual servoing, and using our own design reverse Cara, which is a bit similar to the one that you see there, which is one that I did install in the 90s in a big factory in Montreal. For tube manipulation, for palletization, I would cycle time of 6 seconds. Here, the cycle times we're talking with the ones we did with laser bars is about 1 second, and it's very fast. And it's high precision, 50 microns, and over large workspaces. So we did the first micro manipulation robot over large workspaces. We did the first in the world, really reaching results which are now going in operations in a real industrial process. Now, parallel robotics is my main subject, which I started to do as research when I went to Switzerland at the EPFL. The advantages of parallel robots is they are more performant. First, they can handle large payload to manipulate a mass ratio. Because they have high stiffness, they don't have much mass because they use parallelism. And the fact that they are parallel allows them to be a lot less massive, to be very high in stiffness. So this means they have low inertia, and then you can send all the energy and the torque to the end effector, meaning high dynamic performances to the end effector. And meaning that you need to implement less powerful actuators and you save energy and money, and you achieve much better. Here are a few examples. Those what we call Schoenflies motion, so translation plus 1 or 2 rotations. These are the robots I worked on when I was in Switzerland at the EPFL, Professor Clavel. In the 90s, he was the best in parallel robotics, and he was based in Lausanne, and I worked with him for 2 years. So I worked on the parallel robots here that you see, which are called the Delta, and became the ABB Flex Picker, and now is now copied by every company in the world. And the robot I did with him is the one that you see on the right here, which is called the Manta. And now I work on design of very important Schoenflies motion parallel robots with Dr. Damien Chablat from CNRS in France. CNRS is another network of very advanced research centers which are comparable to Cambridge or Oxford and places like that in terms of levels of engineering and research. Okay, so I started to work with Professor Clavel on lower mobility robots the ones that you see there, the Canuck on top and the Manta. I work with the students, a project, and we design these properly. So we can still apply those, we can still improve those in different projects, and they can do very high-speed manipulations. And then I went on to do a PhD at the INRIA in France, and I used the novel hexapods that you see there, and that was done by a company, CMW Marioni, and it's used in roughing by Peugeot, okay, in near Belfort. And I tried to improve these robots to simulate, and I provided the first kinematic solver that could solve the parallel robot kinematics problem. And it's still the ones I worked on, and not only in computer algebra, and not only in Grosvenor basis-based approach there, but the one that with genetic algorithms afterwards, and the work I did in Spain afterwards for the GIM, geometric iterative method. Those are the best methods still in the world. Okay, so we worked on path planning and following. I completed the robot simulator, a complete one, the first one. We introduced CNC controls with line following, with all the paradigms that go in there. We did position and speed controls analysis. Publications about speed controls is still pending. I did not push the papers out yet, but I can talk about position controls in details, and papers were published. Certifications of tasks, deviation analysis. That's my thesis work. Now I came to realize there were problems with these robots, especially in the mechanical designs, because if you want to have a very good system and if you want to increase performance, well, you have to know that you have to increase the quality of the design itself. So I went on to do different types of approaches there. One of them was to go for cheaper approaches with the planar parallel robots, which were not very well exploited at the time. So when I did have some master students there when I was in Canada. I did design the robot that you see in the middle here for test tube filling, and we did a very nice robot for a very cheap price, around below $5,000. And later on, I did the robot that you see on the right with Professor Roskam at Ostfalia Hochschule in Germany, which is an engineering school, engineering university. And we designed this, and it's running at the moment with the microcontroller technology, both of them running with microcontrollers technology, showing that it can work. It can do all the tasks and all the activities with the 2 layers of controls that you find in parallel robotics, well and efficiently. In this case, the first one in the middle there works with LabVIEW, and the other one works with an interface on a computer, but and linked to MATLAB. So we could do simplicity, precision, low cost, microcontroller based, without singularities, with high accelerations. We could fill in test tubes very well, much better than the very expensive machines which are sold in the world at the moment. And we could do fast palletized network as well. And we could even sketch draft here very precisely and very efficiently. That's work that I've done. And then, knowing that we had problems with some of the elements of the parallel robots, I tried to design systems which would tackle with the problems. First of all are the linear axes, which are not very good and produce a lot of errors. So I designed my own linear axes, which are the result of deployable through structure networking. And this is very rigid, and it does a full range of motion. I have videos which shows that in half a second. Okay, so full range of motion in half a second for a linear axis, that's unbeatable. That's very high accelerations. We went to 16 Gs, but we know that we can go up to 20 Gs with these devices. Okay, and we could design that appropriately. You just need to size the motor properly and make sure the bars have good gearing systems and all kinds of bushings. They're really collinear. There's no issues about linearity. It's working fine. And we worked on the kinematics for that, so you could solve them. Then there was another issue, which when I was working at EPFL, I was working with the people at ETHZ in Zurich, the same type of school in Zurich. And the guys were trying to do a high-speed milling machines, and they tried to design joints, and he couldn't get them to be rigid enough, and they introduced a lot of bandwidth problems, and especially natural frequencies, which would result in a very poor performance and surely not enough for precisions. So I designed these Revolute joints with a student, and they are the most rigid joints that you can find. They are based, they're conical, they're rigid, they're self-adjusting, they have no backlash, and this means as you wear out, they readjust themselves automatically, and they are spring-loaded, so you can adjust them from the spring and make sure you design them with a friction that you already can foresee, and you will be able to apply the types of control to deal with the friction. And we went further. We chose the right material to have the interfaces to remit the friction. We did a universal joint version, which is sketched here, and we have a spherical joint version as well. Pointer parallel robots. That's another issue which I started to work when I was in Cyprus at the Middle East Technical University. People needed energy and there was plenty of sun. So what would be necessary is to go green. And the way to go green is to capture that energy from the sun and to improve it. One way to improve the capture of energy is to be doing sun following with a mechanism which is lightweight, otherwise it's not, it's useless. So I designed a parallel mechanism as you see there. That's a first-hand prototype to show the concept with very simple to find parts from around hardware stores. And we later designed a pointer for fast-steam pointer reconstruction. So you get that on a device that scans the whole situation and quickly rescans that. This robot there is running and it's a very fast one. So it turns like this, okay, very rapidly. And that's one of it's like the Agile Eye of Professor Gosselin, it's as fast as this. And these are the sketches with the geometric iterative method that shows how we can sketch with this, and it's perfect. And you can do the kinematics analysis. And the controls for these kinds of solar trackers, which are very slow and have to follow the sun, we designed a special pulse width control approach there for that. And then we went into reconfigurable tripods. I did the robot that you see below there, which is a 3RPR. And then I did transform the 3RPR with my linear axis. And this is where we were preparing to do. So fast reconfigurable planar robot, high speed manipulation, variable actuation, target any, so can do any task. A robot is a robot, can do anything you wish with this, providing you have a proper end effector. And the goals is an adaptable mechanism, and eventually this would lead to automatic reconfiguration of the robots according to the situations. And then I started to work on drones. I was invited when I was in Canada, and I did 3 PhD students defended in this area. So we started to work, I started to choose the right type of drones because the quad rotors are not efficient and should not be used because they don't last very long, and it's an improper use of energy and torque. So you have to go for quad cruisers like this one done by Airbus. And with these, then you have a hybrid approach there between fixed wing, where you can last long with the wing effect, and you have a VTOL rotorcraft, so you can land and take off from anywhere, and you don't have to worry about taking off and landing as it is a very difficult problem actually for vehicles like that. And you cannot bring them normal fixed wing, you cannot bring them on board a ship, for example, and to go to the North Passage or to go into the Arctic. So fixed wing, double wing, very efficient. And that's what I work on. I'm working on those things with students, and I'm trying to optimize these designs with them and the controls as well, because you have different modes of operations there to make sure that we have an efficient use of these. And the performance is for long durations, and they have to be deployable. And I'm even designing a drone aircraft carrier, which is on an airship design with a student. And then drones to be used in small venues over cities and into situations where we have civil operations like watching over nuclear reactors, inspecting them, or power lines and situations like that, or windmills, wind farms. Well, you need a very good vehicle which can do proper sense and avoid. And I've been working a lot with students on this aspect. Design choices of sensors, external communications, ADS-B, TCAS, and GPS on these robots. And of course, the controls that are good enough and simulation of those controls, certifications of these vehicles so they can be safe in all instances, maneuvers for avoidance. And we worked on these different levels of zones. For example, that's some of the work from one of my students shown here. And you can see there's a drone here. UA and MAC, and you have an intruder in any aircraft, and you wish to be able to detect and make sure you do the right thing at the right time to avoid crashing into an aircraft or any other assets, meaning a lamppost or even a power line, any type of things that you may come across, you have to avoid it. Now, the question of performance, do we have equivalent level of safety? I have a PhD student who defended on that and presented on that. So equivalent level of safety is the big thing, and I can explain and I can work on that aspect. And the beyond line of sight problem, which is more for many countries not possible to obtain. And the team I was working on in Canada was the first civil team to obtain that right in North America. So, and then other mechatronics projects I worked on, these are a list of other projects I work at different time. So I'm working at the moment on stair climbing mechanisms, like the wheels you see that. That's me who made that mechano. That's a CAD of a student that worked last year for me on that subject. I've been working, and I have another idea than this one, but I'm not showing it because I will apply for a patent for it. So stair climbing mechanisms for the household robotic assistant to help the elderly people. In our aging societies, it becomes very important to help the people and to keep them company with a machine that can do something for them. A dog can protect them, but they cannot do a certain number of things which robots could. I'm trying to implement that in wheelchairs as well. And those are two novel designs which were not properly, well, you see them now, but I was the first to show that in the world, you know, on pictures. That's my pictures from 14 years ago. Well, 2005, that's the real year. Then I worked on bong or cork grippers for the whiskey industry and the wine industry, because we have a company here, big whiskey company that is owned by a French company for wine and all kinds of spirit making. Cask level detection, non-opening, so to make sure we detect which casks are of poor quality. I know how to work with these things. I know how to make that. Integration of robotic arm and mobile robots, the dynamic factory. This is something I worked on when I was working in the UCLan in Preston a couple of years, 12 years ago. So automatic reprogramming of robots, as you can see here below, that's a Leyland truck picture from me, which shows the robots painting. And this is actually, I worked on automatic reprogramming with laser scanners and videos and captures with cameras. So visual servoing is a subject that I can work on, and also morphing of 3D clouds to a point clouds as well. So deployable robots, that's a new trend. That's the new big thing that is developing fast for warehouse operations. I'm working with that, and I'm designing things, and I have some connections. I have lots of connections with teams in France and Germany and Italy and Canada. So I'm trying to continue to work with these people towards problem solving these things. Design of a ship running from hydrogen produced by seawater. When I was in Turkey with the Toros University, I was in Mersin, and I had a client who was interested in the green energy, and he wanted me to design a ship that could be run without diesel, and they designed him. The ship that you see running around the world with windmills and solar panels, I've designed one when I was in Turkey, about the same as the one you see, but I showed it in a paper, so perhaps this guy inspired himself from it. But I know how to deal with that. So if you're interested, I'm a mechatronics expert. I can do the systemic approach, or I can approach all kinds of problems, because the system is more important than the details. I'm going for the best details. And when it's needed, as you can see, I can design the best joints. I can design the best actuators. I can design some of those things in depth. I can go for kinematic solving. So I can design in solvers like that. I can use like bond graph or design of experiments. I have a toolbox of very powerful tools there, which can be used to improve the designs and make designs the best they can. And I can show that, and I can use that. So if you're interested, here are my websites where you can access my information, and then some papers available on Academia and ResearchGate, or you can go officially on the venues like IEEE, ISME, and others, and Springer. And you can visit our website here, explaining what I do here. or my former website, which shows what I've done so far, so you can have more about me. So this is me here. If you're interested, please send me an email and I'll answer all your questions. Thank you very much for listening.